Okay, let's get started. So, welcome to the colloquium today. Today we have a very special researcher and guest from Japan, Kyoto, Kazuya Iwata-san.
Yes.
And his background is very unique because he first got his PhD in 2017 in the subject of mechanical engineering. And later, he became a project scientist and the assistant professor at the mechanical engineering department at the Kyoto University. And during the pandemic, he can now go to the lab to do his research on the combustion study. Then he sort of have some interest in astronomy. So he think about supernova is actually also something like a combustion explosion.
Great.
And he started to work on this subject. And during that time, he had published several very nice papers. And this year, he just defends his second PhD in astronomy. So he got his second PhD in astronomy. The astronomy PhD. And he will start a new career on astronomical research. Then he got also the JSPS postdoc fellowship and will go to Germany next year to study the supernova explosion at the Heidelberg. So let's welcome the Iwata-san's talk. And
Okay. So thank you so much for a very great detailed introduction. So it's very helpful. So everyone, good afternoon. Tacha hao and konnichiwa in Japanese. So I'm Kazuya Iwata from Kyoto University, as Kandori introduced, and as the title here shows, my research is special in its focus because compared to the size of the progenitor star, my focus is very specific in the local region, but it has a general importance to interpret the possibility of the global success or failure of thermonuclear transient, today focusing on type 1A supernovae specifically. So that is one motivation to apply my previous knowledge on chemical reaction burning to astrophysical burning. Okay, so I hope you find it interesting enough. So I will proceed to my brief self-introduction. So Ken has mostly already introduced most of the contents shown here, and I'm double PhD holder, so it's very rare to listen to such guys talk, I think so. So both PhD theses are written in terms of detonation topic to address aerospace propulsion in engineering PhD, and to address the explosion mechanism of type 1 supernovae for PhD in science. Okay, there's not so much to talk about this. Okay, so this is a very rough picture showing what I am currently working on. So the main topics consisting of two different topics. The one is type 1 supernovae explosion mechanism, and another is about how the local burning physics is likely in aerospace propulsion device. This is engine designed for using detonation as a propulsion power source. And why I am doing like this is that there is a close analogy between the burning in astrophysical system and in a terrestrial system, regardless of the some intrinsic difference between them. So the one is for thermonuclear reaction system, and another is the reaction system for chemical reaction. But in terms of the hydrodynamics, they resemble each other very closely. Okay, so when we call call the astrophysical burning as thermonuclear reactions, the concept of such burning is ubiquitous and prevalent among all kinds of stellar phenomena. And the most, how can I say, stable case of burning in a convective or distributed way is that occurring in the sun, and as the inner stellar media becomes thermodynamically unstable against the thermodynamic exothermic reactions, it becomes unstable, sometimes representing explosive flame front like this, and this is occurred in type 1a supernovae, which is today's topic, and similar flame front phenomena are known to be occurring in other high energy transient like pair instability supernova as of interest in Kent's research group, and also for X-ray burst. So, okay, my slide becomes also unstable, so maybe explosive. So, okay, let's go on to the next. Showing the how we classify the supernovae to call it type 1a. So this is a classification diagram of supernovae, and the type 1a supernovae is very special in the sense that it is driven by thermonuclear reactions, whereas the other types are driven by quark collapse or gravitational collapse. So this is a common picture for the progenitor system of type 1a supernova, in which a binary system is formed, and there we have the primary white dwarf, and the companion can be anything. So that is not true strictly, but many types of companion star exist as a companion of the primary white dwarf, and until recently, it is, and even for now, it is known that the light curves of type 1a is so uniform, so that it has been believed to be uniform also in the explosion mechanism. But only recently, it has been clear that there are also peculiar types of thermonuclear transients. So like type 1ax or point 1a or something like that. And so it posits diversity of the explosion mechanism of such thermonuclear supernovae. So that is the reason why the unified mechanism of so-called normal type 1a supernovae, which is uniform, remains an open question. And when we call the thermonuclear burning, so it is not enough to discuss detailed physics of burning, because there are two distinct burning regimes according to the propagation speed, deflagration and detonation. And deflagration propagates at a subsonic speed driven by heat transport, while the detonation propagates at supersonic speed driven by shock completion, and you can see from these animations that they are very different in how they look. And the transition from subsonic to supersonic is called DDT, which will be detailed later for my experimental work. Okay, so these terminology are common both in terrestrial and astrophysical systems. So there are very close theoretical analogy.
Ask a question
Okay.
about deflagration.
Okay.
I'm wondering that in the case of deflagration, it means that there is no shock.
Yes. So, strictly speaking, there is a very weak shock ahead of this flame, but it is not strong enough to drive the propagation. Instead, the heat transport, like electron heat conduction or something radiative, would govern its propagation. So, if such a propagation mechanism would come into play, it is called deflagration. But when the shock front ahead of the deflagration, flame front, be strong enough to drive the flame by itself, it is called detonation instead. So that is how.
In the case of deflagration, the burning front and the shock front can be inconsistent, right?
Inconsistent?
The position of
Yeah. So we can define separately the position of shock front and flame front. So yes. So usually, for the deflagration, it propagates at subsonic, but shock front it usually propagates at sonic speed or sometimes supersonic. So it is always higher than the speed of deflagration. So shock stands first and the flame second. Okay. Okay. So this burning front. Okay. So let's look at how this burning front appears very locally in the progenitor system of type 1s supernovae. And this picture, as already shown, is a picture of a progenitor system, and the white dwarf is a size on the order of 10 to 8 centimeter. And by enlarging the part of this primary white dwarf, the burning front generally looks like this. But this picture is not still enough to resolve the smallest spatial scale of the flame front, so we can further magnify it to resolve the detonation front in the upper and deflagration in the lower. And their spatial scale is so severely small, you can see that it could be reach the order of 10 to minus 2 centimeters. So you can see how different their scale are compared to the size of supernova itself. So, and it is easier to imagine now that how it could be difficult to resolve all the relevant scales in one simulation, even with the use of supercomputer simulation, supercomputer resource. Okay, so depending on which of the deflagration and detonation appears to drive type 1 supernovae, there are multiple explosion models as a candidate for explaining normal type 1 supernovae. Because the mechanism of normal type is an open question, as I mentioned previously. And if deflagration is initiated in the first phase in the stellar core, mainly composed of carbon and oxygen, and then transits to detonation, it is called delayed detonation model, which has been conventionally understood as the main pathway to trigger type 1 supernovae. But recently, more focus is placed on the double detonation model, in which as the name suggests, two-stage detonation appears as the first stage as the detonation in the helium-rich surface layer, and this primary detonation subsequently triggers the center core detonation as the second stage. Okay, so this double detonation model has been attracting more attention because it can overcome some controversy, contradiction with observational evidence that the delayed detonation model has experienced. So yeah, so more studies are now focusing on this double detonation models, like this paper result published in Nature this year. And they simulate the binary star evolution prior to detonation onset. They also included the onset of detonation, which yeah, like this. Okay, so now the helium detonation occurs, and somewhere in this movie, the second detonation is presumed to occur. Okay, so sorry, I'm not sure about the details. So okay, so what I want to claim here is that about their resolutions. The resolution level is as the most recent related studies do so. It's on the order of 1 to 10 kilometers, which is much larger, coarser than the required scale to resolve the frame length scale. And okay, so this combustion system has analogy with terrestrial combustion, and terrestrial combustion scientists know well that such low resolution in the simulation of burning could lead to forced ignition, forced propagation of the flame front. So this is very problematic because it may be in some cases that ignition is successfully observed in simulation, but it could be totally false depending on the numerical resolution and some other related numerical techniques. So so you may imagine such very local ignition or failure would not so greatly contribute to the global outcome, but that is a very critical problem, and we have to make efforts to work on this problem. So that is my one of my motivations. And in the combustion, terrestrial combustion, field, how many masses inside the flame region is probably the most frequent question asked about this discussion on terrestrial combustion simulation. And okay, so as I showed previously, it is still demanding for self-consistent, fully resolved simulation to resolve all the relevant scales. So instead of depending solely on such simulation techniques, some theoretical and even burning experiment would benefit in some aspect through the analogy as a combustion system. So another merit from understanding of terrestrial burning is that understanding of terrestrial burning is well established in a good harmony with, among theory, experiment, and simulation. So the fact that we can do experiment can be a strong proof, or we can actually observe this phenomenon. So this can be should be true for the simulation result. We can say like that. So this is a strong can be a strong tool to understand the global outcome of supernova. So that is another motivation for my research. Okay, so the introduction section is almost over. So I will then go on to the contents of my research, and prior to that, I should say that there are two different pathways to trigger detonation, two distinct regimes to trigger detonation. One is direct initiation, which is mainly associated with double detonation model without the deflagration stage prior to detonation onset. That is direct initiation. And the other is deflagration to detonation transition, or DDT in short. This is mainly associated with delayed detonation model. And in this initiation pathway, flame is initially started, ignited as deflagration, and later transits to detonation. So for direct initiation, so theoretical description is much simpler, and we can use it directly. So for this region, I took approach from theory and with a combination with local simulation. And for DDT, the theory are much more complicated, and even the state of the art terrestrial combustion simulation on DDT yes, I related study uses simulation techniques, so simulation and experimental techniques. So that is why I took experimental techniques to address this topic. Okay, so to derive the theories for estimating the ignition threshold for detonation, the most important scale in the detonation is cell width, which is characterized by the transverse propagation of the bifurcated shock front. So there is a main shock front standing normal to the propagation direction, and there are also transverse wave at the bifurcated part of the shock front and propagated like this, forming the fish cell-like patterns. So this is a reason why it is called cell. And it is commonly observed in astrophysical detonation system, as was confirmed in our previous study, and also was confirmed in other researchers' studies. So, so this is yeah, usually it is very difficult to estimate quantitatively the spatial scale of the reaction, but with the use of such observable cellular widths as a characteristic reaction scale, we can derive the theory using cell widths as a characteristic length scales. So that is why this is important. Okay, so the description of, I don't go into detail about the details of direct initiation theory, but I can introduce this only briefly. And this theory is described in terms of minimum energy required for directly igniting detonation. And this formulation, minimum energy, is described depending on the theoretical propagation speed of detonation, and also cell width as introduced in the previous slide. So this is how the cell width comes into play to predict the ignition threshold. So okay, I omit the explanation for the detailed part, but the underlying principle is not so complicated. We just assume the certain spherical diameter of the hot product in which the thermodynamic state of burned gas is assumed, and when we all integrate the internal energy and kinetic energy included in such frame sphere. So we can estimate we can derive not so complicated, but we can take a simple process to derive this equation. Okay, so in terrestrial combustion, it is known that this ignition theory is in a very good agreement with experimental results measuring the initiation energy required for direct initiation. And another theory exists as to quenching threshold, and quenching should be discussed separately from the ignition threshold, because even if the ignition of detonation succeeds, there could be some situations in which ignition occurs, but it fails to get a stable propagation. So for this reason, we need another theory to predict quenching threshold, and it is described in terms of cell width and the wave curvature of the detonation. So by the wave curvature, we mean the global curvature radius of the detonation, like as observed in curved channel experiments, like shown here. And okay, so I don't go into detail either for this theory, but we use this theory to predict quenching threshold. And prior to theoretical description, we run some 2D hydrodynamic simulation to observe cell width for each condition occurring in the surface of the white dwarf. So density and composition is explored by changing the helium mass fraction with the rest mass fraction going equally to carbon and oxygen. Such condition is assumed, and other numerical techniques, a bit simple approximation networks composing of 13 isotopes included presently. Okay, so how much time is left? Okay, 25 minutes left or so. 20 maybe. Okay, so we have much time left. So by doing a series of such simulation for the exploration range of the condition of helium mass fraction and the initial density of the mixture of helium and carbon oxygen mixture, we could get a series of data for cell widths for each condition as denoted by symbols in this graph. So we have limited data on discrete points in the explored condition, and to predict the cell width, which is unexplored, like this, we must predict according to the approximation rule, which is so empirical. But we can predict it based on the 1D theory, and we can use 1D based theory to predict the reaction scale involved in each condition, and we can find the good correlation, almost linear correlation between the 1D reaction scale and cell width observed in each simulation. So for this, we used approximation formula to predict the unexplored condition, and which is in a good agreement with the explored condition, like you can see in this figure. Okay, now we get a database for cell widths in the condition likely to occur in primary stage of the double detonation in the surface layer of helium envelopes. We then go to validation stage of this theory against existing previous study on related helium detonation. And in their study, they put the hot spot which is artificial hotspot radius on the at the base of helium envelope. That is the usual techniques used in most of the previous studies. So that is not self-consistent, but it usual techniques to initiate helium detonation by hand, and they changed the radius of this hotspot size to investigate the minimum hotspot size, which is shown as a vertical axis, changing the center temperature of the hotspot size to predict the minimum hotspot radius as denoted by symbols and dotted line as shown here. And also shown are solid lines. These are our theoretical prediction based on the formula shown previously, using the database of cell widths got from 2D simulation. And the agreement is qualitatively good, as you can see here. Not quantitatively in some parts, but it is surprisingly good considering how the condition and understanding are different depending on its terrestrial system or astrophysical system, and the gap between these combustion fields are linked together by finding these results. So this result was published last 3 years for physical review letters. Sorry, I forget to show the reference. And another theory showing the quenching threshold was also tested for existing previous study, doing some series of hydrodynamic 2D simulations predicting the success circle, the failure of detonation by changing the core mass and the envelope mass. And these three symbols are their simulation results, and their so blue lines denote their theoretical prediction. They made their theory by themselves to predict the threshold between success and failure. But the agreement is not good in their study. But the solid lines are our theory, so it is a far better agreement. You can see here. And okay, so sorry, I will omit the explanation for other helium mass fraction, but okay, so another validation was done against the last year's work by Shen et al., who investigated some mixed condition of the helium envelope and core carbon material. So such a situation could occur in a dynamical accretion from the companion star. When the dynamical accretion hits the surface of the white dwarf, strong convective mixing occurs between the carbon material and helium material. So they consider the equal mass fraction of helium and carbon envelope, and they conducted some 2D hydrodynamic simulation to predict success and failure by changing the core mass and envelope mass at the base of the envelope, and they predict a surprisingly small amount of helium layer to initiate detonation, which is much smaller than the upper limit mass for the normal type 1A. So that upper limit is on the order of 10 to minus 2 solar mass, but they predicted 10 to minus 3 solar mass envelope can even succeed in double detonation. So that was surprising, and we can test how the results were reasonable by investigating the use of our theory, which is denoted by solid lines, and except for one failure case, the agreement is very good, delineating clearly between the success case and failure case. Okay, so our validation stage for predicting ignition and quenching is almost complete, so we can now get the strong method to predict the success and failure of the double detonation, especially for helium detonation, I mean. So, sorry. So we also investigated the minimum, in terms of minimum initiation energy shown for each composition against envelope mass, and each differently colored lines are shown for different combination of core masses from 0.8 to 1.1. And different compositions are tested for pure helium and mixed with core material. And you can see that for pure helium mixture, minimum initiation energy is very high. So it's as much as the order of the energy deposited by dynamical accretion or the explosion itself, 10 to 50 in erg. So you can see that it is how difficult it is to explode a pure helium detonation in the double detonation. But instead, once we mix the material with the internal core, the ignition becomes much easier. On the even on the order of 10 to 40 in erg. So okay, so by the use of terrestrial theory, we can say that mixed composition is much easier for igniting double detonation. Okay, so we can succeed for helium detonation. And how about the stage of secondary carbon oxygen detonation? So what is confusing about this stage is that there are multiple cell sizes in one reaction system. So similar situation happens also in terrestrial combustion system for special choice of mixture, and it can happen in carbon and oxygen system. So I mean by this that the reaction scale for carbon and oxygen, and even for silicon burning to form iron element group could be much different by several orders. So which of the cell scale or reaction scale we should use? We have no answer because the number of related study on such multiple cell sizes is very limited until today. So okay, so we are not sure about it, but we anyway extend it by using both of the carbon scale and oxygen scale. So as we did it for helium envelope, we made our approximation curve for estimating the cell size based on the previous hydrodynamical result on such cellular detonation for carbon oxygen material. Okay, so and okay, かな? Yes. Okay, so we did the same similar thing as we did in helium hotspot, and there are some previous studies who did same initiation techniques using hotspot, changing its size to estimate the minimum required size needed for initiation of carbon oxygen detonation. So such results are shown by symbols here by colored, and in some cases they only observed failure in one density condition as denoted by here. And we are still not sure why it happens, but it turns out to be that using the theory using the carbon scale is not a good match with previous study. But once we use the oxygen scale cellular widths to predict the ignition threshold, the agreement is very excellent. And we have not yet reached a conclusion as to the why. So we are now investigating the reason for this. But yeah, we can say, okay, the theories of ignition also succeeds for carbon-oxygen detonation. So it is very encouraging because we now get the useful method both for primary detonation and secondary detonation involved in double detonation. Okay, we can now predict both ignition stage. And in terms, this result is almost the same, but the minimum initiation energy is shown instead, and the horizontal axis density is converted to the white dwarf mass because so in the assumption that this density is so appears at the base of the envelope. No, in the center of the white dwarf. Sorry. Okay, so now the ongoing discussion for direct initiation in the double detonation looks like that, and the remaining part of my talk will be about the experimental counterpart working on deflagration to detonation transition DDT associated with delayed detonation. And this page generally describes how the DDT looks like in terrestrial combustion system initiated as low-speed laminar flame, then transit to turbulent, and on the way of its acceleration stage, local explosion happens, and then the steady detonation propagates in the final stage. That is how the DDT looks like. And the conventional study on terrestrial combustion DDT has been mostly done in a closed system, I mean a pair of opposing solid walls. This is the most frequent style of experimental DDT. But when you imagine the condition for DDT occurring in type 1 supernovae, you can soon understand that the condition is very different because there is no wall confinement in stereomedial. So in such condition, when the researchers of astronomers, flame scientists are asked, like, is the delayed detonation model possible? So in turn, is the DDT possible in such stereomedial? When they asked like this, astronomers would say yes, because the observation tells us so. So observational evidence is the strongest proof, of course, in the astronomy field. So, their observational result is in a good agreement on the assumption that the DDT happens on the way of type 1 supernovae, especially on delayed detonation model. But when the flame scientists are asked in the same way, they would say, no way. DDT cannot be happen. In such open media, there's no wall, no DDT. So that is how they claim. Oh, so okay. So how can I say? Okay. Okay. So the claim of flame scientists is based on the reason that for in triggering DDT, wall confinement has a crucial role because if you have a wall confinement, the amplification of the shock front is much easier by the reflection of the shock. So repeated reflection of the shock front of the wall easily make stronger shock in front of the frame. And on the wall confinement, there is a boundary layer, do you know? So a low velocity field, so which makes turbulent eddies on the wall, so which makes a turbulent acceleration, which makes much easier the frame acceleration to supersonic. So without that, they claim that no DDT happens. So, but still, there are very limited studies of such DDT in unconfined open media because they just believe it cannot be. But even though they believe so, there are no not so limited experimental studies so far. And yeah, there is a little bit in other related study, and there are some studies claiming that DDT can happen without the assistance of wall confinement. They proposed their theory for predicting DDT, and they claimed, it is a great agreement with the experimental study. But you can easily see that it is still wall confined, so it's not perfect as though. So okay, so yeah, so there are limited evidence on unconfined DDT, so that is the motivation to conduct a DDT experiment. I think it is very rare for you to see such experimental figure. So yeah, we set up experimental apparatus in that only a short duration of the experimental time unconfined system can be realized. So yeah, so you can you can imagine, you can assume there is a wall confinement, so it is not unconfined. But when by limiting the test duration to the order of it is not written here, sorry. So 100 on the order of 100 microsecond. So it is within the time limit in which the disturbance from the wall could not interact with the flame evolution. So we can choose the time scale to realize unconfined-like situation. So that is what I did. Okay, so this is a clear image what we are doing, and we observation techniques are described here, although I do not go into detail, but I did use some high-speed image, so-called Schlieren high-speed photography, which resembles in some parts to interferometry observation, which is used in astronomical fields. So it is used to observe the density gradient induced by the flame front, and it looks like for this spherical frame evolution. And in the exploration range for unconfined flame, the ignition occurs on the center by the pair of the copper electrodes by imposing high voltage, like occurring in automobile engines. Ignition start. Okay, so the same movies. And this darker region represents deflagration. And when we investigate its flame propagation speed, it is much smaller than the sound speed. So unfortunately, in perfectly unconfined system, we could not get DDT. But some tricks was used. So in the assumption that there could be some situation in stellar media that high density, so there is a convective flow in the cellular media, so that high density material and low density materials are mixed in one region. So in such a situation, high density material could have a role as some obstacle to disturb the flame zones. Okay, so for the limitation of the experimental apparatus, we inserted the metal plate looking like this by supported by metal shaft. And it looks like this, and the flame evolution then looks like this movie shows. Deflagration starts, and as it go around the metal plate, it suddenly transits to detonation. Okay, we can show you again. Deflagration and okay, so as soon as the flame develops along the edge, DDT happens on one side of the flame edge, like this very luminous region happens. So this luminous region corresponds to the high luminosity appearing from a detonation. This is how it looks like. So, okay, so so far we can say that in perfectly unconfined system, no DDT happens, but once some disturbing source is placed in one place, DDT could happen. So some disturbance is important, we can say, from the results so far. So this kind of disturbance could be brought by introducing some turbulent flow. So you may know in cellular media, convective flow sometimes induces randomized flow pattern, inducing a turbulent flow. So in such situations, disturbing of the flame front occurs, which could, in some cases, hopefully lead to DDT, even in perfectly unconfined DDT. So that is what we are planning to do in the future work. So hopefully the encouraging outcomes will come soon. So okay, so please look forward to it. So I'm also looking forward to it. So okay, so concluding remarks are so simple. So okay, so we can use terrestrial combustion techniques and theories to predict the global outcomes of type 1a supernovae and related thermonuclear transient. That is a useful understanding. And focusing on local phenomena does not look so straightforward to understand the global outcome, but it is very useful, which I showed here. So, okay, that is all from my talk. Thank you.
Any comments or questions about Iwata-san's talk? And
Thank you.
So is it possible that astrophysical explosion can be treated as some kind of confined DDT?
Not likely, I think. But in one situation could happen, not so for the carbon oxygen detonation happening in the center of the white dwarf, it is not likely to be in closed system. But for surface detonation, so you know, so helium and carbon exist, so low density and high density exist at one location. So in some situation, high density carbon oxygen material could come into play as obstacle-like load. So yeah, so that is what I and Keiichi Maeda, my collaborator, are discussing, and you are not accurately sure how likely it happens, but we only assume, imagine such a situation could happen. Yeah, so that is useful suggestion, I think. Thank you.
Any other questions? some comments on this detonation part. I really think this for the experimental detonation case and the astrophysical detonation case, the environment is intrinsically very different. In terms of first the scale, and also the scale will affect, for example, the Reynolds numbers. So probably in the astrophysical condition is likely to develop more turbulence environment. And actually, I think why when you put obstacle in the experiment, then you start to observe the detonation. Not actually. I think the key thing is your obstacle actually will deflect a shock wave or deflect wave. Deflect wave is very important because once you deflect the wave, the wave will be convergent. So the wave will not propagate homogeneous isotropically. The wave will be convergent. And the converging wave, when two waves colliding, that will trigger.
Yes. So that
burning will trigger the detonation.
That is very good point. Thank you for your suggestion. And so, that is a more common way for triggering DDT. So by focusing shock in a convergent ways, and when the collision occurs at one side, very strong compression occurs. So hotspot is formed to trigger detonation onset. But so that things, the underlying mechanism we are now thinking is a bit different in the point that it is more divergent. So divergent or it lifts up the obstacle. So it is not the situation to form convergent shocks, but instead, so the entrainment of unbound gas into the frame could come into play instead. So that is a very trigger for this DDT.
For example, you can replay this movie, then now.
Okay. So that is easier to.
So the key thing is that when the wave propagate to the obstacle here, and will be bending through the obstacle. And we're bending the through obstacle. Some of the wave will hitting on the plane and
but so we did another experiment. Just one-side wall. We considered a very large one-sided wall, but in such situation, no amplification of shock front occurs. So
because you see, you need to the occurs at a very kind of along this.
Okay. Going around to the
like this scale. You see, but it is not in symmetry, so you have an ignition here. But you see, later you have an ignition here.
We are not sure about how the ignition occurs here. But we are only sure about the very initial instant of initiation, but we are not sure about what occurs here. So just maybe.
And also, if you want the obstacle in the experiment here is the analog, but maybe not really the good, because for even the turbulence environment in the sterile interior, because usually is still not a low Mach number environment.
Low Mach number
means
low Mach number.
So it's the Mach number less than 1. So with the less than 1 condition, the turbulence is not supersonic turbulence. Turbulence only driven very small density fluctuation.
But
much smaller than what you have almost like a very low gas environment with this metal shell. So that's very different condition.
So quantitatively, yeah, many things are different as you suggested. And for your initial suggestion about low Mach number turbulence, so yeah, so even if it is a low Mach number in its speed, so its role to accelerate the subsequent flame is very great too. And so we did, sorry, I hope I can show you other results. So we are doing some other terrestrial combustion simulation on such turbulent combustion. And in such situation, strong shocks are formed ahead of the flame front. So no DDT occurred in such situation where we have not yet reached successful condition, but the success in flame acceleration and the formation of strong shock wave as occurring in normal wall confinement system is also we have observed in such low Mach number turbulent situation. So that is an encouraging result because we can maybe observe subsequent supersonic transition. So for such supersonic transition, turbulence itself doesn't need to be high speed. So low speed would in some case have a better contribution in some cases as so far as our result shows so far. So but we are not sure about the reason why. So yeah, we
so
are
you can
also
have a diffraction wave with a shock wave in front.
yes, if the turbulence exists even in perfectly unconfined.
And then what happens in that situation if you have this? Because the diffraction is the shock, the burning front moves subsonically.
Subsonic, yes.
The detonation means this moves subsonically, and the moving of the front is driven by the burning after
so
push them. But you form the shock wave in front of this front, then shock wave will automatically likely to ignite the burning in front of the original burning front. So I was
that is how the
that's why
final DDT trigger occurs. But so how I can say どうしようかな。So yeah, so you are wondering why. So I want to confirm your point. So
maybe when you observe the shock forming in front of the main front, then the detonation already occurred. That means right after the shock front will become burned.
So even if the strong shock front occurs, it's not detonation itself. So I'm not sure.
Because if you have a strong shock wave, then you will have like a jump shock if it is a strong shock condition. So jump shock condition, your temperature sudden increase.
Yeah, sudden increase.
For a tropical nuclear environment, your burning might suddenly ignite.
Yeah.
So when the shock wave swap the material, it will burn very rapidly. And this burning will push the shock.
Yeah. Yeah, that happens.
Yes.
Actually, in turbulent conditions.
Yes.
Okay.
And also, I think using using this energy on the hot spot, it may not be a very good idea in my point of view. Because you see, you have some energy like a super high, like a 10 to 51.
10 to okay. So yeah, no. So it just was very low White dwarf situation. So
this is not a very good number.
So for this range, so it could be reasonable, I think. So so it's just that for. Just in the context of direct initiation, so not relevant to the delayed detonation. So it's just discuss the possibility of the direct initiation of secondary detonation. So for realizing such direct initiation in double detonation model, the result would indicate that heavier white dwarf would be needed. So, but for this range and the minimum white dwarf mass, as Kenshin or the researcher suggested, ranges around this. So yeah. But so this might be reasonable. I think.
Because the key thing is these numbers.
Yeah. So for
you make these numbers, this number ignition minimum initiation energy. This number is much larger than the supernova explosion energy.
Yeah, so it cannot be. So yeah, it is just a failure condition.
Yeah.
Yes.
Yeah. So that's if people show to stability, you will not very.
Yeah. So we have to show that for this lower mass range, so it cannot be. So yeah, we should say so.
Yes. Okay. Sorry. And no other question. That's thanks speaker again.
Okay. Thank you.